Hello, I'm Donald O'Hare, and this is my recording for Lab 5. So I chose to model the video of the Slinky being dropped and falling in GlowScript. And the most notable part of the video is that when a Slinky is dropped from being held, the bottom of the Slinky doesn't move until the top of the Slinky lands on it. And I chose this because it demonstrates an interesting concept of how contact forces relate to time in real systems. So the motion is like this because it begins in static equilibrium, meaning that the net force on every part of the Slinky is zero. And looking at the bottom of the Slinky as an object and looking at the top as a separate object, the magnitude of the tension on the bottom is equal to the force of gravity. So, and that makes the net force zero. But when the top is released, it is only being acted on by gravity at this point. Well, I mean, along with other forces, but I mean, the main force is gravity, the one having the greatest effect. But the bottom still feels the tension from when it was being held, and it will continue to feel that tension that is equal to the magnitude of gravity, but equal and opposite to that, until the top connects with it, and then they both fall. So in GlowScript, I modeled the top and bottom of the Slinky as their own objects and then put a spring in between them. So the net force for the top was gravity, and the net force for the bottom was set to just be zero, since tension and the force of gravity equal and opposite canceled out. And only the top needed to be updated in this loop because the bottom and the top, I made it so they would kind of stick together after they collided, so there wouldn't be like the top wouldn't just go through the bottom and keep falling. And then I use the same velocity position update formula as we have in every other lab in the wild. So due to the simulation being built around this phenomenon, I was able to get it faithfully rendered. But in real life, it's important to note that there are a lot more factors at work, such as internal spring force, there is internal friction, drag, but none of these play as big of a role as gravity and tension do. So I chose to just leave them out because I felt that they would create a lot of complication, especially since we don't know the exact specifications of the Slinky either. And for this, for the purpose of this, everything time was pretty relative, and so was the weight of the Slinky. So I just set the mass of each ball equal to 1, and then none of those really mattered for this purpose. And because they don't have a significant effect on the movement of the top. And it doesn't matter how fast the top is moving, just that the bottom doesn't. And then here's a video of it running, slowed down. Sorry. So what does it mean? It means that there can be a delay in the transmission of contact forces through real objects. Because we can see that the tension force continues to exist inside the Slinky until it completely collapses. And as mentioned in the video, the same concept applies in reverse, meaning that the part of the object that isn't connected to by a contact force won't feel that until the part that does catches up to it, so to speak. And this couldn't be modeled with just a center of mass point particle system because there's just no way to see that how the two different parts of it move separately with a system like that. So it has to be a real system to model this. So in conclusion, this lab demonstrates how tension, any contact force, and theoretically any force in general can act on real systems in a staggered way. And we can see that anytime a force isn't acting on every single part of an object equally, there's going to be some mismatch. Most of the time, it's not noticeable, but as you can see with the Slinky, there are cases where it's very important to take that into account. And it's important that we understand where this comes from and why it exists.